All right, we're at the last section of chapter 4. It has to do with what they call antiderivatives. Okay, I'm going to make two videos out of this and describe in the first one what are they looking for? What's an antiderivative and the nature of finding them. And then the second video will deal with what the author's calling differential equations. Okay, so they give you a function and you're supposed to, antiderive your way to, say, the original function. So let's explain that. Okay, very quickly. Did you know that the derivative of, say, goofing around tangent is secant squared? Of course you did, right? Here's the thing. You can go the other way. I'll say it in English, the antiderivative of secant squared this function secant squared x is tangent x. Okay, what's the symbology for that? For derivatives, we got d dx, we got tangent prime and all that stuff. In this one section, we're going to do something like the following. So, given f of x is equal to secant squared x, its antiderivative is, and then you can use like a capital letter, oftentimes you do, f of x is tan x. But wait, here comes theorem 1. Couldn't it be tan x plus 2? Couldn't it be tan x minus pi? Couldn't it be? In other words, who says it doesn't have a constant? Because here's the thing. If I derive tan x plus 2, I get secant squared x, don't I? If I derive tan x minus pi, I still get secant squared x. So when you say, I've got the antiderivative of this function, the answer is no, you have an antiderivative. We don't know that you have the one we're looking for. And so what we do is we talk about what they call the general form of the antiderivative. And I'll just use this example, okay? The antiderivative of f of x is equal to secant squared is, and then you can still use the letter f of x like that, and you write, oh, it's tangent. But here's the thing. You tack on a plus c, okay? And what that says is that plus c is saying, you can have plus 0, you can have plus 2, you can have minus pi, you can have any constant added to it, and those guys all qualify as functions whose derivative is secant squared. Okay, you really should, for this particular exercise or video, open your book, pause the video and open your book to page 352. Okay, and when you do, you're going to see a little table there. Actually, it has quite a few what they call antiderivative formulas, but let me tell you, you know them all, okay? Or most of them, let's just say. So for example, if I had a function said y is equal to sine of x, or let's say cosine of x, easier, and let's use the letter again. Let's say that f of x is equal to cosine of x. And we're looking for his antiderivative. So we're going, what's the antiderivative? So what that really means, I'll think over here in the corner here, is that when I find f prime of x equals blank, when I find this guy, f of x is blank, it has to be that f prime of x, when I derive it, is cosine of x. Okay, so we're going, well then what's the function whose derivative is cosine? And you would answer sine. When I derive sine, I get cosine. And that's correct. So you would put down your answer. You go, my antiderivative is cosine of x, but the most general form is plus c. And you're going to want to remember that plus c. People go, oh, yeah, I always have to put a plus C when I do that. But there's reasons for it, huge reasons when you go into the end of our semester, and especially in this section when we're looking for differential equations. And that'll be the second video. So there's a whole slew of these guys finding their antiderivative, okay? You play around with people. What if I had g of x is equal to, say, 5e to the x? Now, it's interesting with a constant. When you derive, it doesn't matter. So you're thinking, well, gee, if I have g of x is equal to, I don't know, but what I want is g prime of x to give me 5e to the x, okay? Then you have to think, well, what would do that? And the answer is, I don't know if it's obvious to you, but we're going to make it obvious after a while, is it's still 5e to the x and then plus c. Because when you derive 5e to the x, you get 5e to the x. The constant, when you derive, is just there for, he's waiting for you to derive, remember? You just go, okay, I'm going to derive 5e to the x, so it's going to be 5 times derivative of e to the x is e to the x, okay? Another one could be something like a lesson here that we're seeing is what happens with those constants. So let's say I had h of x was the number, or let's say -7, and you decide to hit someone with a secant x times tangent x. So again, you're thinking, well, okay, what the heck is going to go on here if I've got h of x, okay, is equal to what, so that h prime of x is equal to -7 secant x times tan x. Can you dream it up? Pause the video and go, what would it be? Okay. Well, I'll tell you what it is. I'm thinking, what guy has a derivative of secant tangent? Derivative of tangent is secant squared, derivative of secant. Oh, it's secant. So what we're getting is, guess what? The -7 just hangs on, and then we have secant x, and then we tack on what? The plus c. Now there's one thing, okay? There's one more thing you really want to know, and that's how powers go. Powers of the variable, okay? So I like to kind of show it this way. If I take a derivative of a power, let's say I do x to the 9th or something like that. Well, we know what the derivative's now. It is 9x to the 8th. What if I decided to go, I want to go anti-derive in this direction? What is the function whose derivative gets me to x to the 8th? Okay, so I'm thinking, f of x equals what, so that f prime of x is simply x to the 8th. Okay, well, there's a good way to look at that. Here's x to the 8th, but he's not alone. If I sent that 9 over here as 1/9, that would do it. Okay, so if this were, say, somebody's little function, and I was looking for the big function, the antiderivative here, I would say the antiderivative is 1/9 x to the 8th, because I'm going to leave it to you. If I derive, don't I have, 1/9 x to the 9th. When I derive that guy, don't I have x to the 8th? And so going in this direction, look what the form is. If I want to take this guy and find his antiderivative, that's what I'm going to do. It's going to be the next power up, because when you derive, the power goes down. But you also divide it by that power. So let me, before these examples, write that out up here at the top. You know that when you derive a power of x, let's say x to the n, you get nx to the n minus 1. Now here's the thing. When you antiderive, and we don't have a symbol for that yet, but we will. When we antiderive x to the n, it's going to go to x to the n plus 1 over n plus 1. That's a nice formula. This is for deriving, and this is for anti-deriving. All right, let's get cracking. Remember the story about the constants. Remember the coefficients. Remember the story about the power of x. Okay, we're going to do a few examples and then call it quits on this particular video. So someone says, here's your function. Here's our first example. What we want to do is find the antiderivative of that guy. Let me show you how this goes. You ready? Well, the first term has got a 4 in front of it, so I'm going to write 4 times, and then I'm going to antiderive the power of 3. So I'm going to show it to you in steps. I'm going to go, that means I'm going to bump up the power by 1. If I'm anti-deriving, the power grows by 1. When I derive, the power drops by 1. Okay? Makes sense? But then I also derive it by that new power. Okay? So think of deriving this thing. Well, maybe not yet. You'll see. At the end of this, when we're done, I'll say, okay, now derive it to see that it matches up with the function we started with. We'll go down the line with this polynomial. Plus 2 times, you want to help me with this one? Now this one's going to be x to the whatever the power is, up 1 over up 1 downstairs. Go to the next guy, you get minus 5 times, what power of x is x? It's 1, isn't it? So this is x to the 1 plus 1 over 1 plus 1. No one does it this way. You just mentally add 1, okay? But we're going nice and slow on our first example. And then what about the 4 plus 4? What happens there? Does it drop off as 0? When you derive, it does. But when you integrate or anti-derive, what happens? I'll show you, for instance. If I had to derive, what happens if we I'll do it this way. The question really is, f of x equals what so that f prime of x, in our case, is 4? What function gets derived and all you get is 4? Think, think, think. Ready? 4x. Makes sense, doesn't it? When you derive, you lose the x, it goes to 1. When you anti-derive a constant, what do you get here? An x. And then don't forget what? There could have been a constant at the end too. So cleaning this guy up, we have the antiderivative is looking like 4 times x to the 4 over 4 plus 2 times x to the 3 over 3 minus 5 times x to the 2 over 2 plus 4x plus c. And we'll just deal with those fractions right now. So f of x is cancel x to the 4th minus 2/3 x plus 2/3 x to the 3rd minus 5/2 x to the 2 plus 4x plus c. That's the antiderivative. This antiderivative stuff does so much, so many wonderful applications, useful, and you'll see why next chapter, okay? So right now we're just practicing this idea of, we know how to derive now, let's anti-derive and see what we get. Just don't forget the powers go up and then divide by the power. Here's another example, but for this one, just like in differentiation, I should write it as powers of x so that I can get going on it. So this x thing is 2 to the, what power is that? I've been teaching that in intermediate algebra lately. What it is the 3 over 5 power minus x to the negative 1/2. You see how algebra plays a big role here. So we're going to go for the, right away, the antiderivative of this bad boy. Okay, here we go. So we're going to write 2 times, I'll put this in red. Here we go, you ready? X to the, now you really might want to see this, 3/5 add 1 over 3/5 add 1. What? That's right, the power goes up. Remember, there's the rule. Minus, and then we do this guy, x to the minus 1/2 plus 1 over minus 1/2 plus 1. Now, those moves become very routine next chapter. Maybe not right now, but next chapter you'll be doing it pretty swimmingly. So cleaning up, we've actually anti-derived what I forget? Plus c, put them on there. So g of x is 2 times x to the, oh no, fractions, 8/5, man. Okay, do you see the 8/5? That'd be a calculus student's going like, I get all that, but how'd you get 8/5? And that becomes, well, that's just fractions, man, over 8/5. You can do it on a calculator these days. Minus x to the 1/2 over 1/2 plus c, okay? And so we're getting an answer of g of x is equal to 2 times 5 over 8. How about inverting and multiplying x to the 8/2? Is this typical? Absolutely it is. That's a minus 1/2, right? So it becomes minus 2x to the 1/2 plus c. And then, you know, a step or two with experience, you'll just be buzzing through this stuff pretty easily. So let's cancel the 2, and we get a final answer of maybe 5/4 x to the 8/5 and minus 2x to the 1/2 plus c. Then if you want to write it as radicals, you can. I tell my algebra students those radicals, hey man, everyone does it with fraction powers. Okay, got one more for you, and then we'll end the video. You can pause it, but this is how you antiderive, and here comes this last example. It has nothing to do with a polynomial, right? It's actually kind of an easy one, but the trouble you might spy is, yeah, I think I have a handle on secant tangent. That rings a bell, but what the heck is that? Okay. Oh, I thought I fixed that. I guess I didn't. Let me fix it right now. That's actually a typo. So let's do this. So, and I'm going to give it away too. H of theta is 4 secant theta times tangent theta. And what I'm doing is I'm changing the problem 1 over cosine squared theta. Okay? And so scribble that out. Okay, so we're looking for this guy, but what you should do first, sometimes you just have to do that. The author likes to mess with us, okay? But what I'm going to do with that 1 over cosine squared is there's no quotient rule that we've talked about. There's no product rule. And you know what? There isn't any in anti-differentiation. So what you got to do is like, how about if I just flip that over? Secant squared theta. Do these expressions ring a bell? Secant tangent, secant squared, yeah. What you're going to do is you're just going to simply go, man, I got my answer right away. The antiderivative of this guy is 4 secant squared, derivative tangent, secant squared. This is secant, we already encountered him, plus tangent plus c, and that one's done. Okay? So that for me is the first video, I believe. The next one goes into the that stuff. So we'll see you at the next roundup.